you see it?
Yeah.
Okay. All right. So today I'm going to talk about spectral sleep scoring, which is something I've been working on for the past few years. I'll talk first about the difference between low versus high deep sleep, as I call it. And then at the end, I'll talk about spectral versus visual scoring, sleep scoring, and how they compare. So these are examples of the devices that I've been using. On the right is the old device that I used prior to this current study. And it's 2 channels on the forehead referenced to the mastoid. The one on the left is the one I'm using right now. Ideally, it's just stuck to the forehead with no headband. We're finding right now that in order for the PPG to work properly, we need to have a headband. So they're working on a solution to that, to go back to just the patch, which is very comfortable to wear multiple nights, and it doesn't disrupt your sleep. And this one is referenced like to each other, locally on the forehead. The one on the right, I actually ended up doing a referential reference anyway, or sorry, a reference forehead to forehead, because the mastoid would produce too much high frequency noise. So the data that I'll show is comparable in terms of reference. It actually doesn't really matter that much. It's just a matter of the noise that is produced from the mastoid. Okay, so this is an example of a healthy sleep report. So I'll just go through the components. This top one is 1 channel of EEG from the forehead, arranged from frequencies low at the bottom, high at the top. It's the same data. These 2 top panels are the same data. The dominant frequency one in the middle there is a blue dot placed every half second for the dominant relative frequency at that moment. And so that is helpful to see the patterns of sleep across the night, even when the amplitude of the oscillation might be low, as in REM or wake frequencies. So what you can see is when you're awake, your brain is going sort of gamma frequency, and then it literally falls down to lower frequencies, and then goes back up and comes back down, and goes back up and comes down. So these are sleep cycles. In this case, so you can see that the first 2 cycles dropped to what I call high deep sleep, between 1 and 3 hertz. And then in the 3rd cycle, it drops to what I call low deep sleep, which is a dominant frequency below 1 hertz. And then the next cycle goes back up, comes back down to low deep sleep. The next cycle is kind of a flat one. It goes to REM and then goes into what I call light sleep, which is when spindles are most dominant, and kind of hangs out there for a while. This is typical. Usually one finishes their deep sleep at the beginning of the night. Then REM starts to be elongated towards the end of the night. And then this person went back into low deep sleep towards the end of the night, which is not super typical, but is, I guess a normal variation. It's not common, but it's not pathological. The sleep looks otherwise fine. And then finishes out the night with REM, which is generally what you want to wake up from. Okay, so what's the difference between delta or high deep sleep and slow oscillations or low deep sleep? So this is a picture of slow oscillations or low deep sleep. So you can see that it's not strictly sinusoidal. There's an arc that goes up to the top and then drops precipitously straight down, and then arcs up again and falls down. If you count the cycles, 1, 2, 3, 4, 5, 6 cycles in 30 seconds is 0.2 hertz. So less than 1 hertz. Below, this is high deep sleep, an example of a stretch of high deep sleep. This is the same time scale, 30 seconds, but a very different y-axis. So the top is 90 microvolts, the bottom is 70 microvolts. So there's a huge difference in amplitude. If you take 2 seconds out of this high deep sleep and you blow it up, you can see a little bit more of the sinusoidal activity there. It's a lot more jaggedy because the amplitude is much lower, so you're seeing other frequencies mixed in. If you count these, 1, 2, 3 in 2 seconds, this is 1.5 hertz, which is the range that I call high deep sleep.
Judy, may I ask a question?
Yeah.
Can you go back 1 slide? Yeah, the scale on the top panel, it says 900 microvolt. Let me confirm this again. So the EEG recording here is basically a bipolar from both frontal head part, right?
Yeah, this is this is a reference basically from here to here.
I see. And is this number correct? Like 900? Is this true?
Yeah. I mean, so these are massive. I mean, not everybody's are this massive, but this is an example of an extremely massive.
Really? Wow. Okay.
Yeah.
Wow. Okay, thank you. This totally changed my understanding of EEG.
Yeah, it's a different world in sleep for sure. Okay, so this is another example. I'm going to go through a few examples of healthy sleeper reports so you get an idea for what these typically look like in a healthy situation. So you can see this sleeper had 2 cycles of low deep sleep, clear stretches of REM sleep, and then finishes out the night in hour 4 or 5 with just light or high deep sleep, and then finishes in REM sleep. This is another healthy sleep report. You can clearly see the low deep sleep cycles again. This time I added.
There's a question.
But you use very low pass filter, yeah, for this data.
There's no filter on this data.
There's no filter. Okay, so this huge difference in the on that previous plot also comes from this very slow oscillation, yeah.
I'm sorry, the top panel.
When you were the plot Makoto was asking about.
This one.
Yeah.
Yeah. Right. So this is raw data.
Okay.
Yeah, and the reason you can't see any other frequencies is because the scale is so massive. I mean, there's faster frequencies riding on those, but you just can't see them.
Okay, and
with your
time scale here, it's multiple hours. Yeah, this is the whole night.
39.
Oh, this is just, yeah. I mean, this is the 30 seconds of a whole night.
Ah, this is 30 seconds only. Okay. Okay, sorry. Thank you.
Oh yeah, sorry, yeah, just 30 seconds.
Julie, one other question. Like how did those kind of stage diagrams you're showing, how do those map on to traditional sleep staging? Like which one?
I'm gonna show you some examples at the end.
Okay, great.
Yeah.
What is traditional slow wave sleep? Would that correspond?
Okay, yeah. So traditional scoring goes wake, and then N1. You slide into non-REM stage 1, and then non-REM stage 2, and then non-REM stage 3. So they only have sort of N1 is very brief, and it's just kind of like you're getting sleepy, and then N2 you're actually in light sleep, and then N3 is deep sleep. And that's all they have. Oh, and then REM, of course.
And like when people talk about slow wave sleep, what frequency do they mean usually?
Anything below 3 hertz.
Okay. So, okay, got it.
Everything, yeah.
So they don't distinguish between the low and high.
Right. And I'll show you why I think that's absurd. Yeah. Okay. So here I added EDA or electrodermal activity. This is recorded in the inside of the wrist, and this has been known since the 60s that EDA follows what they called deep sleep, but they most of the time follow deep sleep, and you can see when deep sleep starts, it ramps up and then it falls precipitously right at the end of the deep sleep cycle. The amplitude varies from cycle to cycle. I don't know why, but you can see that it does ramp up during deep sleep and falls afterwards. But it's not all deep sleep. It's only low deep sleep, not high deep sleep. And that's why probably they didn't find it in all deep sleep, because they didn't know the difference for some reason between low and high deep sleep. But so this is one of the reasons why I thought that these are physiologically different stages, that they are doing different things and they have different physiological characteristics.
So what's your unit of this EDA?
It's microsiemens.
Microsiemens.
Yeah, that's from the Empatica.
Oh, okay. Because this is very interesting. A company in Japan called NeuroCare, they actually developed this pillow that will form an electromagnetic field. So sort of like when you are sleeping, you are in the magnet of the scanner. And then also they use EDA and to turn on and turn off the electromagnetic field so that you can uh, help people to get into sleep. They turn it off. And then when they detect you are in REM sleep or awake, they turn it on so that they will put you into sleep.
Okay, so it helps facilitate sleep.
Yes.
Mm-hmm. Interesting. Okay, so anyway, so you can see that the first cycle, clearly high deep sleep, no EDA. Second cycle, low deep sleep, very strong EDA. Here's another example of a healthy sleep report, where you can clearly see the low deep sleep that's associated with EDA. The EDA, again, different amplitudes for different cycles, but it always comes up every time there's deep sleep, low deep sleep. Here's an example of it's one of these very clear things when you're looking at the data like this, the difference between REM and non-REM sleep. Non-REM sleep has spindles, REM sleep does not. So the easiest way to find what's REM sleep and what's not REM sleep is to see if there's spindles there or not. If there's no spindles and there doesn't seem to be any strong gamma activity, then it's most likely REM sleep. And you can see it very clearly when you look at, the data in this way. Okay, so what are slow oscillations? So they generally start in the front of the head, although they can start anywhere in the cortex. But when you average it out, they usually start closer to AFZ, which is around your hairline on your forehead. So this is a diagram of a slow oscillation. You can see the negativity start in the front of the head, reach a nadir at the bottom of the slow oscillation, and then when it reverses, that negativity shifts towards the back of the head. This is another display of the same thing, a bunch of channels on the head, and looking at a cross section, you can see that the slow oscillation travels backwards from the origin up in the front of the head towards the back of the head over 80 milliseconds. This is a display of the time frequency plots around a single slow oscillation and at different spots on the scalp. So the ones with the slow oscillation superimposed are where the origin of the slow oscillation was. And so you can see where the slow oscillation occurs, there's a low frequency burst. But what's interesting is this spindle that's nested in the rebound of the slow oscillation. And that turns out to have real consequences for your memories. So slow oscillations, as it turns out, strengthen memories, while delta sleep, or high deep sleep, weakens memories. And this is a summary of a very complicated animal study that I won't go into, but suffice it to say, when there's spindle nesting inside a slow oscillation, there's preservation of the memory reactivation. And when the same thing happens during delta oscillations, so the middle two blue ones, there's a weakening of that memory activation. And then when the slow oscillation comes around again, there's spindle nesting, and it leads to preservation of that memory. So one of the ways that they think that this could occur is by sharp wave ripples in the hippocampus. So this is a diagram of a mouse brain where slow oscillations occur or start in the cortex. Spindles are nested in that with an interaction with thalamus. And then the sharp wave ripples are thought to be triggered by a connection from the cortex to the entorhinal cortex that then stimulates the hippocampus to produce sharp wave ripples. And those are memory reactivations that have been stored in the hippocampus that day. Okay, so what I found in my first study with the PTSD sleepers was that they were lacking low deep sleep in far more cases than control sleepers. So you can see that those dark red blobs that I showed before, so to remind you, up in the upper right hand corner, that's a control sleeper. You should have big red blobs. You should have these spikes in EDA. You can see no blobs, no spikes. But their sleep is very well organized. You can clearly see the cycles. You can see when they're in non-REM sleep or in REM sleep. But just don't make it into low deep sleep. This is another PTSD sleeper who lacks low deep sleep, but has some low frequency activity during REM. But I think this is REM and not low deep sleep because there's no spindles. You know, you can clearly see the spindles before and after, but not during that. And the character of the EDA is different from the normal EDA. I mean, first of all, very low amplitude, which may or may not matter. But when you look closely at it, it's a very spiky type of activity that I actually suspect in this case is just an emotional reaction to a dream, because EDA is typically used during wake situations to measure emotional reactivity to stimuli. That's what it's used for in the daytime. For some reason at night, it follows deep sleep. Who knows why? But I actually think that this is an example of what we typically think of EDA for is emotional reaction. Okay, so what I found was that on average, PTSD sleepers had less low deep sleep and more high deep sleep. It was actually just completely like flipped. So, you know, about 16.5% of the night in high deep sleep for controls versus 21.7 in low deep sleep. And then PTSD sleepers, about 21% in high deep sleep versus 17.4% in low deep sleep. But when you add up the high and low deep sleep, their percentages were identical, meaning that deep sleep was conserved, but the balance between high and low deep sleep was altered between these two populations. So looking at it as a graph, we'll just focus on the high and low deep sleep. PTSD sleepers had more high deep sleep and less low deep sleep than control sleepers on average.
This is for how many subjects?
This one, I think it was about 60 or 80 or something like that.
Is this specific for PTSD, or have you tried other populations?
Oh yeah, I mean, I had no reason to believe this was only PTSD. Like, why would PTSD cause you to not have low deep sleep? I never thought that it could possibly only be them, but I didn't really know. Now that I'm looking at these databases, I think it's pretty common in sleep pathology, because I see it very rarely. Although, you know, sometimes it's hard to say if, you know, I'm not seeing it because the electrode is too different, too, you know, far from the slow oscillations or something. But no, I think it's very common, and it definitely, I think, should be looked into more. Okay, so a second study that I did at the same facility. So this is at the VA Aspire Center, which is a residential facility for basically for PTSD, where they stay for months at a time to help with their PTSD symptoms. And so I did a second study there, basically the same thing, but added a urine sample to see if there was any correlation between, you know, any physiological factors and their low deep sleep. But so I found the same thing, that they were, again, lacking low deep sleep, but their high plus low deep sleep was conserved, but just, you know, this opposite pattern from the controls. But what I did find was that melatonin dose correlated with low deep percentage. So the higher the dose of melatonin they were taking, the higher their low deep percentage. I didn't find this in the first study because almost nobody was on melatonin in the first study. So it's just like a luck of a new medical director who prescribed melatonin more and was able to find this. The effect was conserved even when I controlled for a number of other medications that they were on, as well as their SpO2 level, to say. So their blood oxygenation. And incidentally, I also found for the second time that prazosin and sertraline both decreased REM percent when they were present. So, which sertraline is not a surprise. That's established in literature. Prazosin is used for nightmares and to decrease nightmares. And I don't know, it looks like it might just decrease REM so that they have less nightmares, which is, I guess, good in the short term, but not great in the long term, in my opinion. Okay, so the current study that I'm working on is just working off that last result of the melatonin correlation and taking within subject a baseline week of 4 nights without melatonin, and followed by the next week 6 nights using melatonin, and then 4 nights washout, to see if, you know, within the same subject, I can manipulate how much low deep sleep they get. And that study is just at the beginning. I've only recorded 7 subjects so far, so we'll see how that turns out. Okay, so the question about visual scoring versus spectral scoring. So how does it line up? So this is from a database. This is looking at channel F4. I'm going to show just F4 or F3 in these slides. Okay, so just to orient you, the third panel down says visual scored hypnogram. The dark green is for wake, so both of us have what's called wake. Then they have a stage called N1, which I don't bother scoring. So that one I put in light green, doesn't correspond to anything in my scoring. N2 basically corresponds to my light sleep, and so I put both of those in cyan. There, N3, which is their just deep sleep, all deep sleep, I put in dark blue. My deep sleep is separated into high deep, which is in magenta, and low deep, which is in dark blue. So, so this is a reasonably good correspondence. Now, so here you can see when they're in what I think is obviously deep sleep, they waffle between N2 and N3. And you know, their rules are just different from spectral scoring. It just has to do with the percent of every 30-second epoch being, you know, low frequency or spindle frequency. So when you're looking at 30 seconds, you know, you might have to score it as high as light sleep, even though when you look at it as a full whole night spectrogram and you're kind of smoothing over those 30-second epochs, you can see that it really should be contiguous, I think, that they're pretty solidly in deep sleep in these cycles. But so there's going to be a lot of differences between spectral scoring and visual scoring. And so I just want to point out that I don't think there's really, even though visual scoring is considered the ground truth, it's really not ground truth. It's people looking at squiggly lines. And a lot of times they're looking at squiggly lines that are like the difference between 25 hertz and like 37 hertz, which I don't know, I can't tell the difference between those. So I'm just going to point out some places where there's correspondence and where there's not. So here is fairly good correspondence. We basically got the same deep sleep. I just didn't really waffle between deep sleep and light sleep. I think they're all pretty much deep sleep. But of course, there's lots of spindles because it's non-REM sleep. You always have spindles throughout non-REM sleep. Here, I have no idea why they would call this REM. There's clearly very strong spindles. I think in this case, spectral scoring won. I looking at the whole night spectrogram, to me, there's no way you could call that REM sleep, because you can see on either side of that where the REM is strong in the 25 hertz range. That's for these derivations, that's where REM sleep is. That's how you can tell it's REM sleep. There's A, no spindles, and B, a density in about 25 hertz. So those two are clearly REM. In the middle, it clearly changes, and how a visual scorer couldn't see that, I don't know. But I do sympathize with it because they're all pretty fast. It's all pretty fast. You're looking at the difference between like that. There's a pretty high spindle. It's about 16 hertz or so compared to like 21, 22 hertz. It's pretty close. So it's hard to do visually, but when you're looking at the spectrum, not hard. Okay, so here's another correspondence. You can see, again, the waffling between N2 and N3 versus spectral scoring. It's usually more solid. And one of the reasons for that is the spectral scoring is done using an algorithm, a hidden Markov model. with expectation maximization, and it favors continuity. So it's always going to be a little bit more smooth than the spectral scoring. Than the visual scoring in more ways than just the fact that it's looking, at overlapping windows. Okay. This one is another example of the difference between REM and non-REM sleep, and how this visual scorer thought this entire thing was REM. They thought this was exactly the same activity throughout all these hours. And again, I've looked at the confusion matrix for this database, and it doesn't look great in terms of consistency, but I think there's a very good reason for that. I don't think visual scoring is always right. So that it doesn't correspond that great is, in my opinion, not a bad thing. All right, so here is again a place where there's clear spindles, but they scored a REM in there. And it's actually hard to tell why in some cases. There might have been some high frequency stuff in the left-hand square there, but it's still not as strong as the spindles or the delta that's really pretty obvious in the spectrogram also. And then here again, REM the whole time. There's clearly cycles going on, and the visual score completely missed that.
Can I ask a quick question?
Yeah.
On the pure slide.
Oh.
So what exactly does the red mark in the bottom of the spectral score?
Yeah, spectral score. Yeah.
So what does that mean?
Yeah, so that is because you can see in the spectrogram at the top, there's some flecks of red here. And that's because during rapid eye movement sleep, there's sometimes rapid eye movements. And because we're recording from the forehead, sometimes that comes out as low frequency activity. And sometimes it's very strong, as I showed in that PTSD sleeper with, what I think is a nightmare or whatever, the dreaming EDA. Sometimes it's very strong. This one is not visually very strong, but it caused the original scoring from the hidden Markov model to say low deep sleep. But I have a post correction for it to see if when it scored low deep sleep, there was an absence of spindles, then it gets rescored to be REM. So
I see.
So that catches that problem of low deep sleep or low frequency activity not always being low deep sleep.
Okay, I see. Thank you.
Yeah, thanks for that question. Yeah, that's a good point. Okay. So this one, it was interesting because, one of the questions is like, so when I score low deep sleep, how is it scored in visual scoring? Apparently sometimes as REM and sometimes as light sleep N2 and sometimes as N3, even though, again, I feel like this is pretty homogeneous period of time here, and the visual scorer saw that as 3 different stages. So yeah, the correspondence is not necessarily that great. So
Judy,
again, here, how this could be REM sleep with
Judy,
obvious spindles.
Judy, quick questions. The visual score actually is based on multiple channels, including EKG. And, okay. And
yes.
the button is only using how many EEG channels?
So the spectral scoring is based on 1 channel, and I have an example of how that can change also.
Okay, 1 channel. It's also the forehead channel.
Yeah, it's a forehead channel, but I've looked at other channels on the head in these databases, and they look kind of the same. I mean, they'll have less low deep sleep as you go farther back, but the cycles look basically the same. I mean, you should be able to see the difference between spindles and not spindles. And they're also looking at muscle atonia and stuff, from the chin, but I don't know. I mean, if their muscle was, I don't know, so in this case, maybe they thought it was REM because they had muscle atonia in their chin. I still think you should have scored that as non-REM sleep.
Well, you cannot change their minds.
Yeah, right. I mean, right. Yeah, I realize this is an uphill battle.
Well, in fact, Winnie actually, she just asked you a question. And she is analyzing data, it's public data from 110 subjects. So, which means she can actually use your algorithm to score them. It's completely automatic, right?
Yeah, it's completely automatic. Yeah.
Julie, I have two questions. So the question number one is that on all those examples you are showing, it looks like during the first hours of sleep, you have rather a high dip and then the low dip in the subsequent. Is it always like that, or it's just a coincidence here?
It's always that your deep sleep is at the first half. I mean, usually I showed the very first one where the person went into deep sleep at the end, which is not common, but I don't know. I don't think it's a pathology, but usually you pack in all of your deep sleep at the first half of the night and REM at the second half.
Yes.
While you cycle through them, it's just the percentage of either one changes from the first half to the second half. The high deep versus low deep, it is fairly common to do, if you're gonna do a high deep only, it does usually happen in that first cycle.
Okay.
And at the end. So but this is all kind of, it's very person specific. Some people fall straight into low deep sleep, and then as the night progresses, they start doing more high deep sleep because
okay.
So it varies, the order of high and low deep sleep, but generally they both come at the beginning.
Yeah, because in all the examples you showed here, the first deep episode was a high deep and then followed by the low deep so far. And here was my second question. When you calculate the proportion, do you control for the overall duration of the sleep?
Well, it's by using the percentage, you are controlling for the overall total time of sleep.
Yeah.
So,
yeah. Right.
Yeah. So, if they slept 4 hours, you're still looking at a percent. I mean, it would be hard though if you sleep 4 hours, you've screwed up your sleep already because you're just not going to get to REM probably. So, I mean, unless you're really habituated to 4 hours of sleep, it's going to be kind of.
I'm asking because if it's if for most of the people during the first cycles you have rather high deep and in the subsequent you have a low deep, then the duration of the sleep will affect mostly the low deep. Yeah.
If you sleep less, so few hours that you don't even make it to low deep.
Yeah, if you sleep 4 hours or 5 hours, you will have less low dip if the low dip comes in the subsequent cycles.
Yeah, I mean, if you sleep 4 hours, you're missing a lot of stuff. But if you only sleep 4 hours, you're probably going to go into low deep sleep first because you're so sleep deprived that you're going to make sure you get it, is my opinion. I've never looked at super short sleepers like that.
Yeah, here's the subject. Me.
Although, yeah, I know Ziping is our 4-hour sleeper. I did have somebody who slept very short, and he was at Aspire, and when you looked at it, it looked actually totally normal, but because he cycled through everything. But then if you looked at the time scale, it was like very, very rapid. It just, when you plotted it like this, it actually looked the same as a normal night's sleep. So he's like, I think, well habituated to sleeping only, I think it was like 4 hours. And he actually went up and down into everything. He had the subjectively, he had the worst sleep I've almost ever encountered, but his cycles actually looked far more normal than other people. So we'll check out Ziping, see how it looks in a well habituated 4-hour sleeper.
So, well, in conclusion, you actually, if you add the low and high sleep together, you have the same percentage, for the normal and PTSD. But it's just the PTSD has deficiencies in low sleep, right? Low deep sleep.
Yeah, right, the deficiency, yeah.
Have you actually tested out their, for instance, test performance, cognitive performance? No. Okay.
No, I mean, I just have, things like their PTSD severity, their anxiety and stress levels, which did not consistently correlate with their low deep sleep, nor did their subjective sleep reports.
Mm-hmm.
I didn't know. I mean, they're also highly medicated, so they actually sleep kind of well. Like they are unconscious for a good number of hours. So I mean, they all say they sleep like crap, but they don't remember anything from it. So
can you replicate that animal experiment where you showed that high and low seem to correlate with different kinds of memory performance?
Mm-hmm. What about it?
Well, you suggested that like that perhaps the high deep sleep is not as conducive to memory formation.
Right.
So maybe there's something you could do. I don't know.
Yeah, I mean,
but yeah.
So yeah, I mean that's been shown. That's people have established this. In fact, I mean there's a whole literature now on trying to induce or enhance the magnitude of low deep sleep so that people will have better memory consolidation. So this has been studied very recently that that slow oscillations enhance memory and that they can enhance it by giving you auditory stimulation to increase the amplitude of your low deep sleep.
And what frequency are they using?
They're just okay. So they're just looking for the pattern of the slow oscillation. So they're basically looking for like massive microvolt changes, and they start tracking it, and then they predict it and give a little simulation at the exact right time to enhance that drop.
Oh, right.
Okay. That's very interesting.
Okay. And so just to give you a couple of examples, so this was, dropped from REM to light sleep, was not caught by the visual scoring. This is an example of right versus left electrode from using, okay, well, this is right versus left. Okay, so you can see that you can have a difference between your left and your right head. So this is getting at Ziping's point. When a visual scorer is looking, they're looking at all the electrodes. I don't know exactly, what they do with this, with left versus right, but it might be a drawback of the spectral scoring, although you can score these very quickly with multiple channels and kind of get around this. But, so F3 has obvious low deep sleep, F4 does not. So for me, I get two different scorings, at the bottom there for F3 versus F4, whereas of course they have one visual scoring for that one night. And I think this is something that you want to get around by looking at as many channels as you can. And usually they look the same. Every once in a while they look very different like this. But I don't know, it is what it is, but I think you can still get a lot of information out. But I do like to look at sort of all three channels. It helps me. So I look at this and this and this, and it helps for me just, if I was going to look as a clinician, then I could see exactly what's going on very clearly, no matter what the spectrogram or the hypnogram told me. And of course, you're not getting the back of the head, but I think it's probably fair that if they have slow oscillations, you're going to catch some of them at the front of the head. Okay, so this is just a little interesting one. We're kind of running out of time here. I think there is a clear pattern here. You can clearly see the spindles, and then it splits between high and low, and the visual scorer said that was wake, and I assume that's because the low, where it split to the low, that's in an alpha frequency, and alpha means awake, but the higher one is definitely REM frequency. So this is like an example of you have a REM frequency and a alpha frequency. What does that mean? There's literature to say that pre-lucid states or even lucid states have a mixture of what's obviously REM and obviously awake activity. This person erred on they're obviously awake because there's alpha. My algorithm is only looking at the 25 hertz, so it didn't see the alpha at all. So that may be wrong, or it may be right. I think there's a lot of ambiguities. Again, I think you should be looking at the actual data to know what got you to this score, to this hypnogram. So this is kind of a similar example, actually, where REM was split between what looks like maybe an alpha frequency and a higher frequency. It's also often split between high frequency and theta frequency, and which wouldn't be as confusing, I think, for a visual scorer. But anyway, another example of what could be ambiguous there. All right, so in summary, spectral scoring led me to differentiate deep sleep into high and low deep sleep. The risk DDA correlates with low but not high deep sleep. In 2 PTSD populations and in this third one, it's turning out to be true that they are showing a low deep deficiency compared to control sleepers. The melatonin dose correlated with more low deep sleep, so I'm testing out whether taking it from 1 week to the next will actually change their sleep architecture. And spectral versus visual scoring reveals the strength of visualization of the whole night of EEG data. So you can see, what produced that hypnogram. And I think face validity, it shows face validity of the spectral scoring, that you're actually, in many cases, getting more accurate scoring, in my opinion. All right, that's it. If anybody has any questions.
I have a question. Are you going to, or is it okay to distribute this presentation slides to us? Because I want to discuss some of these contents with my colleagues. Is that possible?
Yeah, sure.
Thank you.
Mm-hmm.
Yeah, maybe can you actually give presentations next week to Microsoft people? They are visiting us.
Yeah.
Yeah, particularly I think they are interested in the work performance affected by sleep.
Yeah.
Okay, so I will send you the schedule.
Okay.
Okay, any other questions?
Julie, I know you said that the melatonin dose, like more melatonin was leading to more low deep, and that they're trying to figure out ways to like enhance this low deep sleep.
Wait. Can you come closer? I can't hear it. Sorry.
I know that you said one thing you found in terms of correlation was with low deep sleep was the melatonin dose. Mm-hmm. And that they were looking into ways and researching other correlations with how to improve or increase the amount of low deep sleep you can get. What are some of those methods, and like what are some of the things that, do you know some of the things that they are actively researching in terms of how to improve that amount of low deep sleep you get?
Yeah, well, so what's being studied most right now is this auditory stimulation, and some people are doing it slightly different with a little like any kind of pulse will sort of cause it to be lower. And I think it's a little bit like how K complexes at the beginning of sleep are enhanced. Like if there's a noise while you're falling asleep, it can induce a K complex, which is the same as slow oscillations. K complexes are slow oscillations, but at the beginning of sleep, they'll be enhanced by a noise. I think it's the same thing when you're in deep sleep, that a noise will just, for some reason, cause it to be a higher amplitude. So that's the main thing that you can do to increase the amplitude. But I don't know what they do. And I've talked to some of these companies, and I've talked to them about my research, and I tell them, like, not everybody has these slow oscillations. So what do you do if they just don't have it? And they don't know. So I don't know if you can induce slow oscillations when they aren't there, because what they're doing is trying to find where they are and then make them bigger, which is different than inducing it. So I think I don't know that it's recognized in that field yet that they could not exist.
Okay, so currently it's more like increasing the amount that you already have and maximizing that effect, as opposed to, but like not being able to induce them in like the PTSD subjects, for example, that you're not seeing it, so they haven't, that's like further away.
Yeah, so apparently it's the amplitude or the amplitude helps anyway in the memory consolidation, which is what they're testing with these auditory stimulations. But yeah, nobody's looking at what happens when you're lacking it. I'm the only one who's shown that, because nobody looks at high versus low deep sleep. And yeah, and the people who are trying to stimulate it, they were never looking for a lack of that either. So I guess they've never come across somebody who lacked it. I don't know.
But there are studies showing that if you lack deep sleep, what will happen, right?
That deep sleep what?
If you lack deep sleep, what will happen?
What are you asking me?
Yes.
If you lack any deep sleep at all, I don't know. Actually, I had a subject who was like that at the beginning of my study. I've never seen that before. And I suggested he go to sleep study. I don't know what. I imagine it's not good. I don't know. I mean, it's hard to. I think I've come across studies where they've tried to somehow not have inhibit deep sleep, but allow them to have REM or something. But I don't understand how that's possible, actually. Preventing REM is easier because it all happens at the end of the night. But I don't know.
Okay, thanks.
Mm-hmm.
One more question.
So I was reading that the deep sleep is usually related more to this physical recovery, and the REM to more cognitive recovery. Is it, according to the most recent studies is it still true or not?
Yeah, that's the way I think of it. I mean, I think that that it's low deep sleep that is when your brain shrinks and your CSF washes all your proteins, your discarded proteins for the day out of your brain space, so you don't get Alzheimer's and dementia and that kind of stuff. so I mean, that there's a study showing that in humans, they don't call the oscillation that they're looking at a slow oscillation. They just say a deep sleep, and they may even call it delta, but it looks to me like they're talking about slow oscillations and not a delta wave. Mm-hmm. But there's only been one study showing that brain shrinkage thing connected to a large slow wave oscillation. Mm-hmm. And yeah, so I think it's physically the time when your brain is washing out, and then that massive change in potential. I don't know. I mean, I kind of think of it as clearing the slate, like resetting your second messengers and stuff like that. I imagine that's when that kind of stuff is occurring. Mm-hmm. Okay. But nobody's, of course, correlated it with higher low deep sleep because nobody's looked at it that way.
Mm-hmm. Thank you so much.
Okay, thank you.
Sure.
That ends today's lab meeting, and thanks. See you again. I probably will talk to you later this week.